Hi, today we'll continue with the IMU of the Tornado S Russian missile. First, I made some mistakes on the previous schematic. So let's see, first the current source for the LED of the accelerometer here. So there are actually two versions. And this one is the first version, which was replaced by this one. On the first version, the current source uses a Zener diode here of approximately 6.5 volts. There is one transistor here, okay, and a resistor. The current is approximately 40 milliamps. This resistor permits to have a lower VCE voltage, which permits to limit the power dissipation on this transistor. This circuit was replaced by another one. This circuit is present on board dated 2024. The previous one was a board manufactured in 2022. So you can see we have a Darlington. Okay, so this transistor works actually in normal mode. I made a mistake on the pinout of this transistor array. Instead of a Zener diode, there is actually a current source. I thought it was a Zener diode here, but actually it is a current source of approximately 300 microamps. So this gives a voltage across this resistor of 6.4 volts, close to the previous voltage. The current is approximately 33 milliamps here. I don't know exactly why this circuit was replaced by this one. So maybe there is a problem to get this diode, or maybe there is a reliability issue with this diode here. I don't know. The second thing concerns the buck converter. Actually, this part is not a MOSFET. It is actually an equivalent of linear regulator LM317. We can find this circuit in the original datasheet of the LM317. The next topic concerns the circuit itself here. Actually, this is not a multi-slope ADC. It is a voltage to frequency converter. There is a Russian patent here. You can see the reference of this patent. You can find it on internet. This patent concerns the temperature ability of this accelerometer here. We can see here a block diagram of this accelerometer, which is on the left here. So this is the servo accelerometer. What is interesting is not the accelerometer itself, at least for today, but we have here on the right an interface, okay, which permits the measurement of the acceleration itself. So we can see that this thing is very close to the circuit which is on the missile. We can see here the integrator, we can see the two comparators, and here we have several flip-flops, and we can see here the two output transformers. Okay, so we can see here in details the circuit, so we can recognize the integrator here, the two comparators with the positive threshold voltage here and the negative one for the other comparator, and we have here two JK flip-flops, and we have here a feedback, okay, which permits to add or to subtract a reference current here. The input is here. It is a synchronized voltage to frequency converter. We can see the signals here for a clock frequency of 200 kHz. On the top screen here, we can see the output pulse for a positive input current. In the middle, we have the reference voltage. 0 is here. So when the voltage is at 0, we have the integration of the input voltage here. And we can see that we have a negative voltage here. Okay, we can see that the duration here is exactly 40 microseconds. It corresponds to the duration of 8 input clocks. There is of course a jitter because everything is synchronized to the clock input. In practice, this is not a problem in that case because we need to integrate the acceleration to give the speed. The integration is actually the count of all these pulses from a given moment. Currently, the input current is 10 milliamps. Therefore, there is an input voltage of 500 millivolts. So we can see that the frequency is approximately 1.74 kilohertz. I am going to multiply by 2 the input current, 20 milliamps. The frequency is now 4.48 kilohertz, that is to say twice the previous frequency, 30 milliamps, 5.20, 2122 kilohertz, 40 milliamps, 7 kilohertz approximately, 1 milliamp, 185 hertz approximately. For the last part, I will design a circuit which permits to measure the acceleration and also the speed and maybe the position. For that, I will use a circuit I have designed a long time ago for a professional project. Okay, so this is the schematic diagram. You can see the display, big processor, and there are also several input-output here. Okay, so I will use this PIC microcontroller. What we need is actually two counters. One output gives pulses when the input voltage is positive. The second output generates pulses when the input voltage is negative. So therefore I will use the two counters and I will subtract the values of these two counters. I will use two 32 bits counters. One input is pin 6 here, T4CK. The second one is T2CK here. Unfortunately, pin 6 is used for the LCD display, so therefore I will need to select another output for this one, so we need to cut here this line. And we need also a clock output, so I will use actually a pulse width modulation output, which is OC something. Let me see, maybe a pin 18. No, pin 18 is used for this one. Pin 11. Okay, I will use pin 11 here. We have output compare 1. It is possible to generate a clock from that pin here. Okay, and that is interesting because the pin 11 is connected here to this transistor, so it should be possible to drive directly the primary of the pulse transformer. This is the test board for the accelerometer. The accelerometer is here. There is here the marking for the direction of acceleration, okay, which is from top to bottom here. The accelerometer is connected to the middle board here, this one, and this board is connected also to this test board. There is here a pair of wires for the power supply. The power supply is connected to this adjacent board here, the 5 volts. And there are 3 twisted cables, one for the clock, which is generated by this board. The clock is at 200 kHz. And we have 2 twisted pairs of wires for the positive acceleration and the negative acceleration. There is also here a selector which permits to select between the acceleration mode and the speed mode. And there is here a push button which permits to initialize the counters in speed mode. Okay, so we have here the acceleration mode. The first line shows the difference of the two input frequencies, and the second line shows the acceleration in G. So here we have 0 because the acceleration is orthogonal. You can see here we should have 1G. Okay, for a frequency of 326 Hz. And here we should have minus 1G. Okay, so this thing is quite accurate. Okay, we can test the speed mode.